Hi, I'm Corbin Graham from CSC 466, and today I will be presenting on my project, Cloud Computation of VR Applications. This project was proposed on February 4th with the current objective of exploring the network difficulties, as well as the computational difficulties, associated with doing off-site computations of VR scenes and objects. The end goal of the project is to have a very small scale and simplistic rendered VR scene that utilizes both a local computer's resources and an off-site server's resources. I've chosen this topic as someone who enjoys VR gaming and any other projects taken on in VR. I see VR as a new medium that still needs to be explored to its fullest. This presentation has been broken down into multiple sections for how research was taken out on this topic. First, we will look at the network requirements that are set to be a baseline for any attempts to do VR computation. These baselines are set prior to any implementation work and are designed to check the probability of off-site VR computation. For this section, we will look at the required latency, the average size of a VR frame, and the throughput of the network pipeline. All of these values' importance will be discussed in their sections. Next, we will look at the ideas for how to accomplish off-site VR computation. There are a few ideas here that will be looked at individually. After that, I'll look at the methodology for completing the ideas laid out in the ideas section of the paper. This will include more requirements for the completion of this project. We will then discuss the results from testing, and finally, a look at other papers and ideas completing VR off-site computation. With the introduction out of the way, let's look at our first section of interest, a discussion of the network requirements of this project. This section only discusses the requirements and not the solutions to these requirements. Given the complexity of an individual VR scene, I have broken down this section into three main requirements. First, the required latency. Next, the average size of an individual VR frame. And finally, the required throughput of a network pipeline to make the project possible. For latency, we can simply reference other work done in the field. The paper and presentation I have previously done, titled Edge Caching and Computing in 5G for Mobile, VR, AR, and Tactile Internet, from 4 University of Ottawa students, suggests that a latency of 30 milliseconds or less is expected for an online VR game. Of course, this number is specifically referencing online VR games, but we will use it as a baseline since it is on the higher end of latency expectations. The estimation for an individual VR frame is quite difficult and is subject to a large range. A major issue is that any frame rendered in VR is rendered in a higher resolution than anticipated due to there being one screen per eye. As an example, an estimation from another project, titled Conduit, Efficient Video Compression for Live VR Streaming, which utilizes 360-degree 4K video streaming, estimates a single 4096 by 4096 pixel image with 24 bits per pixel is 50.33 megabytes in size. This is a pre-compressed frame size and is also far higher resolution than to be used in this project. However, we will use this as an absolute top-end estimation for a single frame size. Due to the ideas presented in this paper, the average estimated frame size will be 20 megabytes. For the estimation of required bandwidth, we will look at an existing service, Google Stadia, which allows for streaming of video games with off-site computation. Their website offers a chart, shown here, for estimating required bandwidth depending on video quality and other factors. The VR device used for testing in this paper is the HTC Vive, with a total resolution of 2160 by 1200. Therefore, we will place the estimation one notch above the 1080p at 25 megabytes per second. However, this chart estimates streaming to occur at 60 frames per second, but the HTC Vive requires 90 frames per second due to its refresh rate. Therefore, we must multiply by 1.33 to get an estimated 33.25 megabytes per second. Finally, we will round down the estimate, as no 5.1 surround sound will be streamed, to to give a maximum estimate of 33 megabytes per second. This is far greater than actually required. A final note for the requirements is that the cloud server rendering the content must be able to render each frame within 11.1 milliseconds. This number comes from the article Introduction to VR Application Performance Tuning from Intel. The calculation is simply 1000 over the target frame rate, which in our case is 90. The main idea for the completion of this project is to actually split the load of rendering. That is, rather than make the local system or server do full computation of a scene, the load will be distributed. The first method for accomplishing this is to separate the objects that need to be rendered for each scene. The simplest way I found for splitting the elements is by their interactability. That is, any object that the user can interact with is in one category, while any elements that are non-interactable are in another. Workload can then be distributed as either the server computing interactable objects or the local system computing the interactable objects. It was decided that due to the expectation that an interactable object should have instantaneous response and not be placed at the whim of a network, that the local system should do this computation. This logic is compounded in that, to reduce network traffic, the static members of the scene will all be computed on the server. This will be the main method tested and discussed throughout the paper. With this split, it becomes more apparent as to why the requirements discussed in the previous section are likely vastly overestimated for this approach. Another approach, however, and one that would likely utilize most to all of the requirements, is to do all of the computations on the server. This theory is mostly ignored due to high server costs. Next, the paper continues by looking into the methodology used for studying the approach of splitting and distributing the elements in the scene. We must first find solutions that cover all of the requirements laid out in the earlier sections. The local system used for all testing in the paper contains an Intel i7-4770K processor, 16 gigabytes of 1333 MHz RAM, and an NVIDIA GTX 1080 video card. Any reference to VR will refer more specifically to an HTC Vive running 2160 by 1200 resolution, with a refresh rate of 90 Hz. This is a homogeneous system and the only one tested throughout the paper. First, we must satisfy all network requirements. To do this, multiple ping tests were completed against various Amazon AWS server locations. AWS was selected as the server host due to my own familiarity with its offered services. 2 servers were created to do further testing on average response times, one in Oregon State and another in California. The server in Oregon gave an average response time of 90 milliseconds, while the server in California gave a response time closer to 30 milliseconds. The California server was selected based solely on response times and will be the server referred to throughout the paper. Amazon provides a $35 credit for active students. An application to this service was completed, allowing for the usage of a GPU-based system in California. This GPU system was chosen to complete the 11.1 millisecond render time required for VR. This will be the service used for all offsite computations. If additional testing was deemed necessary, and the AWS budget had been spent, an additional computer could be used to perform local network testing on the project. The Unity game engine is utilized for the creation of the basic VR scenes. For the project, Unity version 2019.3.6F1 is used in all discussion. A very basic scene was created, shown here. The scene only contains the VR camera rig, 2 controllers, a ground plane, and 1 interactable cube in the center of the scene. The Unity Profiler tool was then used to gather large amounts of data on the rendered scene. This collected data will be used for interpolation of an implementation. With this data, a series of data packets were created to represent a series of frames. Each data packet is of size 3 megabytes and is placed onto the California server. The packets are placed there to represent scene assets being available on the server. To maintain realism, we must also account for the approximate runtime of rendering the frame. Local machine testing gave us a render time of 8.4 milliseconds, well within the 11.1 millisecond delay required to properly render at 90 frames per second. So we will use this as an approximate render time. To represent this render time, the script, running Python on the California server, will wait 8.4 milliseconds after receiving a ping from the local machine before sending one of the 4 megabyte packets back. Response times are checked and the data is aggregated. With an understanding of this methodology, let's shift to the final results. The results of testing puts us close to this being an implementable solution. 20 packets were delivered with an average round-trip time of 34.55 milliseconds. With the added 8.4 millisecond render time, this puts the round-trip time at 42.95 milliseconds. This is slightly better than expectations, considering ping tests were returning an average response time of 30 milliseconds. One of the larger issues noticed was a massive amount of variance in packet round-trip time. The minimum achieved round-trip came in just 2 milliseconds, with a maximum round-trip time of 93 milliseconds. This large variance could pose massive issues, as consistency is required to keep the FPS stable. Without a stable FPS, the VR system would need to revert to reprojecting frames multiple times, causing a very jittered motion. These results show potential for future research into this topic. With that, let's look at the next steps for this project. The most glaring next step is a full-scale implementation. Accomplishing this requires looking into different approaches for methods of splitting the elements of the scene. The paper presents 3 suggestions for this methodology. The first would be implementing the VR application with the initial intention of distributing the computations. This would involve, during the development of the application, tagging individual objects as either a cloud computable object or a local computable object. This is not an overly desirable approach, as it requires the cooperation of developers to create applications with the intention of splitting the computations. The second is an overlay application that detects the presence of a rigid body within an object element. An element with a rigid body is deemed as interactable and will therefore be rendered locally. Any other object, such as the skybox, will be sent for computation in the cloud. This method suffers from 2 issues. First, the overlay program, while searching for rigid body objects, may be too computationally intense. Second, detection of rigid bodies will likely lead to too small of a load being distributed to the cloud. This brings us to the third, the most complicated, but likely most effective approach, is to do computations dynamically. Computations could be split in a far more dynamic way by polling the available resources on the local system. If the local system is having difficulties keeping up with the renders, begin offloading scene elements to the cloud system until the system stabilizes. This method is far superior to the other 2, as it requires no cooperation of developers and limits traffic over the network. All 3 of the proposed methods need to be explored further. The paper continues by looking at issues faced within the paper. There are a few issues throughout the paper that still need addressing before a full implementation can be completed. First, all testing is completed on a homogeneous system. Other systems need to be tested for more thorough results. Next, a more realistic measure needs to be completed for the size of network data transfer. By this, a more complicated scene is required to fetch a more accurate data size. Another issue is there is plenty of room for pipelining and parallelizing operations that is not addressed in the results of the paper. Finally, the paper is a proof of concept and does not fully implement any solution. A fully implemented solution is still required to validate claims of the paper. The paper's final section is to look into other work done in this field. We will start by looking at one of the papers already mentioned in this presentation, Conduit. This project, from Akash Patel and Gregory Rose, was created with an attempt to stream 4K 360-degree videos more efficiently to VR devices. Their methodology includes cropping the video to only the area seen at the current VR device's position. The project's success managed to obtain a latency of 75 milliseconds and, due to the optimizations of the project, required only 1.8 megabytes per second of bandwidth. Another project, directly from Unity developers, gives us a solution very close to the end goal of this paper. The project, titled Unity Render Streaming, leverages WebRTC to allow users to navigate 3D scenes and stream the results to multiple devices simultaneously. The project works by streaming the contents of a server rendering the 3D scene to multiple users and accepting their input for movement within the scene. The project is not translated to be run on a VR device, but there is likely a solution to be found by extending this project. The project, Edge Caching and Computing in 5G for Mobile AR, VR, and Tactile Internet, is a compilation of relevant work for 5G streaming of VR and AR. Therefore, this paper was a fantastic springboard for the completion of this paper. Although 5G is not yet widely available, it poses to be an excellent option for future attempts of this project. This is mainly due to 5G's low latency and high bandwidth. Additionally, the paper led to Amazon's Lambda service being considered as an additional option for the completion of this paper. Finally, one of the forefront leaders into this field is Huawei. Huawei has already created a massive collaboration to bring to reality the streaming of complex VR and AR content to users' mobile devices. These technologies rely fully on the implementation of 5G networks, and so final results of this collaboration are yet to be realized. Xinhao News suggests that the overall latency of 5G networks is 5 to 8 milliseconds, far below what is required for VR. Several small-scale implemented solutions are shown on Xinhao News as well. To wrap the paper up, let's summarize its contents. The paper's main goal was to look at the potential of cloud computing VR resources to allow for lower-end systems to run VR applications. The paper unveiled the network requirements before undertaking the task. Methodology for the execution of the project was discussed, including the systems used for all testing. The results showed that although bandwidth was not a difficulty, a latency of 42.95 milliseconds would not be quite fast enough to maintain a nausea-free VR experience. Finally, other projects were uncovered in the same field, leveraging emerging technologies to create the desired cloud-computed solution of the paper. It will be exciting to see the future developments into this field and how soon solutions will be available at a consumer level. Thank you.